couple kind of pieces of business, just so that we're all on the same page. Um, so we've got the iteration assignment. Hopefully that went okay. Yeah. Okay. And then the one that's really gonna blow your brains is the recursion. Okay. So don't try and start that on Sunday night because your mind will go right. So we're going to look at a little bit more recursive stuff today, and then kind of transition into the next topic a little bit. And we'll spend a few days talking about sort of basic algorithm analysis and, kind of, which is another, major area of sort of modern computer science. Um, and then we'll kind of finish the semester with some application stuff, so some programming type things, and yeah. We'll also do here, probably not next week, but the week after, I think, the first the core skills exam. We'll talk a little bit more about that later. Um, but yeah, so we're more than halfway through, just barely, but anyway. The other thing is freshmen in particular or sophomores, well, really anybody, but interested in majoring or minoring in computer science? Yeah? What should you be doing at lunch today? Huh? No, it's actually, is it on Zoom or is it in person? Oh, okay. Uh, yeah, so at lunch today, there's a CS info session. Basically, it'll kind of be, what do the majors and minors look like? What different courses are there? Uh, Maybe at least tentatively kind of what courses tend to be offered in which semesters and that sort of thing for planning purposes. So, really, we need sophomores to do that because that's kind of the decision point where you've got to make sure that you're on track and everything. But freshmen, you guys are all more than welcome to come. Um, and the schedule of classes for next semester will be released, I think, next week, like Monday-ish. So you guys can start thinking about next semester. But basically, if you want to continue with studying computer science, next semester you guys need to take CS111. That's basically it. And then if you have not already taken Calc 1, and you want to major, if you've not already taken Calc 1, then next semester would be a good semester to do it, unless you have some other thing planned. Um, well, the one reason not to take Calc 1 next semester, any ideas why you wouldn't want to do that next semester? Well, that's why you might not want to do it, period, is because it's hard. But the reason why you might not want to do it next semester is it's because it's what time? Uh-huh, and with whom? Yeah. So that's definitely a reason not to do it, is because I'm teaching it, right? And McKinney is horrible. So they'll just hire anybody to teach around here. You guys pay how much a year in tuition, and they hire morons like me to run class. So yeah. Anyway, um, yeah. So if you're interested in the CS major or minor, then there's been email blasts, obviously, about the details for today's session. Uh, on the same subject, anybody interested in a math major or minor? Okay. Uh, some definite no's from back in the peanut gallery. But we're going to be doing the same sort of thing for math tomorrow at lunch. Um, so, yeah, so just FYI there. Um, I think that's it from the announcement department. Um, yeah. Okay, well, let's get to it. So last time we were looking at recursive stuff, and so let me open back up Genie. here. And that's not what we were doing. That's what I was doing with my other class. Okay. This was our recursive algorithm for the Towers of Hanoi solution. Okay. And some of the like quotes and pluses and stuff there was really just to handle printing on the screen correctly, but you know, basically don't worry about that syntax stuff. But essentially, what was the solution? If there's one disk to be moved, then what do? You just do it, right? Okay. And if you have more than one disk to move, the way you're thinking about it is moving the top stack, except the bottom one, then move the bottom one, then move the top stack again. Okay, but how do you move the top stack? So like, let's say you're moving 5 disks. How did we think about that? Well, it's 4, 1, 4. Okay, but how do you move the 4? 3, then 1, then 3. But how do you move the 3? 2, then 1, then 2. But how do you move the 2? 1, then 1, then 1. Well, how do you move the 1? Well, that's obvious, right? So it eventually, you just kind of keeps on peeling. And so the structure, right, that we saw, if we, let's go ahead and run this. So we want, oh, I used a capital. Okay, so what did we say? Let me just do, say, 5. Oops. Okay, so so what do we see? Well, here's the middle, right? Okay, so looking, let's either above or below, it doesn't matter because they're sort of symmetric in a sense, right? Looking below that, what do you see? Well, the stuff below what I've highlighted is moving the top 4 of them, right? And then the 5th one was the dude in the very middle, okay? But how do we move the top 4? Well, we've got to move the top 3, and that's these 7 lines here. Then what? The 4th one, which is the bottom one of this top stack of 4. And then we need to move the top 3 again, okay? Well, to move the top 3, what do we have to do? 1, 2, 1, right? So you see how this is sort of a oniony kind of structure, right? Or if we were to sort of draw a tree here to kind of, you know, look at it, what we would see is kind of this sort of structure, in a sense, right? Does that kind of make sense? Yeah. Okay. And the reason that this, of course, works from a computing standpoint is because does the recursion ever eventually stop? Yes. Okay. There has to be a base case to it for it to make sense because otherwise it'll go on forever. And obviously we can't do that in a computing sense. Okay. All right. So let's look at, again, we started talking about this at the end last time, the factorial function, okay? So let me make a new file here, and let me call this, let's see, documents, CS101, oops. Okay. We looked at another example of a recursive thing from that's useful in math and probability and statistics and stuff, the factorial function, right? So what was the definition of the factorial function? What was 5 factorial? Right. Okay, so 5 factorial was defined to be 5 times 4 times 3 times 2 times 1. Okay. We could leave out the times 1 because duh. But but anyway, we'll just leave it at that. Okay, but what's the observation with that? Well, if 5 factorial is 5 times 4 times 3 times 2 times 1, well, what is 4 factorial? 4 times 3 times 2 times 1, right? So 5 factorial has a copy of 4 factorial inside of it. Similarly, 4 factorial is a copy of 3 factorial inside it, and so on down the chain, right? So the recursive way to think about this, okay, is to say that if you have, and let me just sort of write this in a comment. Huh? What is it in Python again? Oh, that's right. Okay. So it tells you how often I'm writing Python code, or at least this semester. Uh, I'm writing all C and just a crap ton of assembly. Yeah. So don't worry, you guys will not be spared assembly. You guys will get some at the end too, right? So assembly is this stuff, right? Doesn't look too bad. Here's maybe a more fun one. Yeah. Yeah. It's what you have to look forward to if you want a CS major. Yeah. So, okay. So the way we would say this in math class, right, would be n factorial equals n times n minus 1 factorial. Okay. Now, actually, this does bring up kind of an interesting point because the factorial function is maybe it's the only one I can think of at this exact moment. Okay, but when do you normally say the name of the function when you're doing like applying it to a number? Like you'd say f of x or square root of x or something like that, right? Normally the name of the function gets stated first and then what you're applying the function to gets stated second. That's backwards with the factorial function because when do we put the name of the function? The second, it's the exclamation mark, right? And off the top of my head, are there any other examples of this in math where we do that, where we put the name of the function at the end instead of at the beginning? Maybe the modulus operator? Yeah, but anyway, I just think that's kind of interesting. Okay, so that's how we would write it in math class, okay? What we want to do is look at how would we write this sort of thing in a computing sense so that we could ask the computer, hey, what is 10 factorial? And it'll return whatever the number is, okay? So that's the math class definition. Okay, so what we're gonna have to do, okay, I'll just call my function fact for short, but factorial, okay? And what kind of number is it gonna take in? It's gonna take in some number, okay? And what should I call that number that it takes in? Well, in X, whatever, that doesn't really matter, just pick something, okay? Okay, so the def here means that I'm defining what fact of n means, okay? And this is how you define functions in Python. Okay, so what is, if we go back up to math class, is this, is that enough of a definition or am I missing something? What am I missing? Okay, that's certainly very important. We'll need that, but it's missing something, namely base cases, okay? Because if all I do is tell you that n factorial is n times n minus 1 factorial, you'd be recursing forever, right? If I asked you 5 factorial, does what I've got there in my comment tell you when you get to stop? No. Okay, so when do you get to stop with the factorial function? At 1 or 0 for that matter, okay? So what's our base case? What is 1 factorial defined to be? 1. Okay? So I need to add that fact in, and we need to use the two of them together. Okay? So 1 factorial is defined to be 1. Right, okay, so when we come into our function, the input number is either 1 or it's something bigger. Okay, if it's 1, what's the answer? Well, 1, right? So how do I check if the number that came in is equal to 1? Well, what's that code for? What are the next two letters I'm about to type? If, right? If what? What am I interested in seeing if something is? I want to know if n is equal to 1. Okay, so what do I need to type next? Y2 equals, Kiani, that's correct, but why? Okay, so what's the difference between double equals and single equals? Just as a, yeah, okay, so the difference is a single equal sign assigns the value. So if I said n single equals 1, that would say, okay, the variable n now has the value of 1. If I say double equals, this is asking a question. Is it the case that n is the same as 1? And what's the answer to such a question? Either yes or no, true or false, okay? So it's always a Boolean, meaning that true or false, okay? All right, so if n is equal to 1, what's the answer? 1, right? Okay, so if the input number is 1, the output number is also 1, and that's easy. Okay, so we return 1, meaning 1 comes out of the function, okay? Is that okay? Okay, what about if the number n is bigger than 1? Then what? What do we return? Well, what's the recursive definition up at the top? Yeah, n times n minus 1 factorial, okay? And then the way we'll have to type that is return n times fact of n minus 1, okay? And why is it fact of n minus 1 here? Well, what's the name I've given to my function? Fact, okay? And what are we passing to the function for n times n minus 1 factorial? We're passing n minus 1 to the thing, okay? All right, so notice that the fact function is defined in terms of itself, right? That's what makes it recursive, okay? So is that okay? All right, so let's run this and see what happens. Make sure it works, and that I haven't screwed something up. Okay, so are we okay with the code here? Any questions about what I typed? All right, so hand on your head when you're ready for me to run this thing. Kiana, you're not ready for me to run it? Yeah. Okay. Yes? Good? Cody, wake up. Well, but then you took it off. Uh-huh. Okay, so the stupid case, what is fact of 1? And sorry, it's down there at the bottom. Well, what is 1 factorial? 1. Okay, so that works, right? That it at least correctly gets the base case. What's 2 factorial? right? What's 3 factorial? What's 4 factorial? 24. Do these numbers look correct? Okay, and so, right, this thing gets big very quickly. Okay, right, it's a very fast growing function. It's even faster than the exponential. Okay, but does this look like it's working okay? Yeah. All right. So how is it computing the 100 factorial, right? Or 10 factorial. Let's just take 10. That's not so horrible. How is it doing this? It's saying, okay, 10 factorial. Well, that's 10 times whatever 9 factorial is. What's 9 factorial? 9 times whatever 8 factorial is, and it's going how many layers down the rabbit hole? 10 layers, right? Because I'm doing 10, all right? And for the 100 here, how many layers is it going down? Basically 100, right? It's 100 times whatever 99 factorial is. Well, what's 99 factorial? 99 times 198 factorial. And so, right, and this sort of turns into the, 99 bottles of beer on the wall kind of thing. Although who puts beer on the wall? Right, has anybody ever wondered that? We have that stupid song, but who puts beer on a wall? Huh? Well, who drinks beer? People that are of age. Mm-hmm. I know some beer is kind of gross, especially the beer you guys like to drink, namely cheap beer. Right. Okay, so what would happen if I put in a bigger number here? Okay, so what happened in this case? Right? Yeah, it exceeded the maximum recursion depth. Okay, that's a limitation of my computer more so than it is a limitation of the idea of the factorial. Okay, and this, by the way, is not the only way to code the factorial function. There are other ways to do it, but this is sort of a good way to kind of, again, continue to understand recursion. And yeah, so anyway. Now, that said, look at what 100 factorial is. Very big. So what do you think 1,000 factorial is going to be? Just astronomically ginormous, right? So anyway. Okay, so does that kind of make sense? All right, so let's look at another kind of recursive example and see kind of what's happening there. All right, so let me define another function, okay, and let me put this in. How many of you guys have ever heard of the Fibonacci numbers before? Okay, what are the Fibonacci numbers? Right, okay, so the sequence is, let me just type this, right? The sequence of Fibonacci numbers is 1, 1, 2, 3, 5, 8, 13, 21, etc. Okay, how do we generate all of these things? Okay, well, the first two are given, 1 and 1. Okay, what's the next one? 2. How did you get 2? It's 1 plus 1. Okay, then look at the next number. 3 is what? 1 plus 2. 5 is, all right, so what's the pattern here? Each new number is the sum of the two numbers prior to it. Okay, so our factorial function was recursive in sort of one sense, right? And this one is recursive in sort of two senses because it depends on two prior numbers instead of just one. Okay, so if the recursion depends on two prior numbers, how many base cases do we have to have? 2, right? It's got to match, right? If it was 5 layers deep, we'd have to have 5 base cases, okay? But we don't, okay, for this example. All right, so that's our sort of mathematical pattern, and now let's figure out how we need to code this, okay? So I'm going to make my function, and just for shorthand, I'll call it fib for Fibonacci, okay? And what's our base case here? If the number coming in is 1 or 2, right? So, okay, let me rephrase here. If I ask what is fib of 5, what am I really asking? What would be a reasonable interpretation of that question? What is the 5th Fibonacci number? Okay, so according to my list here, if I asked what's fib of 5, what should be returned? 5, because that's the 5th one in the list. And if I said what's the 6th Fibonacci, it'd be 8, the 7th would be 13, and so on. Okay, does that make sense? Okay, so what are my base cases then in terms of my input number? The input number is what? Number 1 or number 2, okay? So if I'm asking what is the first or second Fibonacci, I don't have to do any thinking. What are those two defined to be? 1, just period, okay? So what I need to do is I need to ask the question, do I have the number 1 or do I have the number 2? Okay, well, if all I wanted to check was do I have the number 1, what would I type here? That, right? If what I wanted to check was if, oops, the number was 2, I would type this. And what do I want to know? Okay? In English, what do I want to know? Is the input number equal to 1? Is it equal to 2? What's the English word that needs to go between these? Or. Okay? Because I'm asking, is it 1 or 2? Okay, so you remember when we did those logic gates and stuff? Yeah, remember OR gates? What does it mean for OR to be true? One of them or the other one is true. What about if both are true? Is OR true? Yes, it is. XOR isn't, OR is. Now, in this case, can both be true? No, that doesn't make sense because you can't have a number be 2 different values, right? Okay, so what's the, in programming languages, right, what's the symbol or how do I write OR in a programming language? Well, this is one of the things that makes Python so nice. What do you think I'm going to put here? How about just the word OR? Okay, that's really nice that Python just uses English for a lot of its stuff, okay? Other languages, C, for example, would use double vertical bars for OR, just to keep you on your toes, okay? But Python is sort of nice in the sense that it just uses plain English for this. Okay, now let's then make sense of why it needs to be a logical thing like the word OR. So n double equals 1, what is that really doing? It's a question, right? And it's saying, is the value of n the same as the number 1? And the answer from such a question is yes or no, true or false, okay? And same thing for whether or not n is equal to 2, right? Again, It's a question. It's asking yes or no, true or false. How do you combine things that are true and false? What kind of operations can you do with things that are either true or false? You can do the logical operations, okay? And what are all the different logical operations that we looked at way back? And, or, not, XOR, NAND, in XOR. I'm missing one. NOR. I did say NAND, okay? Okay, so all of those things are logical operations in the sense that what do they combine? They take in two things that are either true or false, and they return something that's either true or false. Okay, so does that kind of make sense? Yeah, vaguely? Would it make more sense if it were 10 in the morning instead of 8 in the morning? Yeah, possibly. I don't know, if you guys want, is anybody in student government in here? Yeah? You could campaign to eliminate 8 a.m. classes. You could. It wouldn't do you any good because you're about to be out of here, right? So, I mean, back in the day, right, I think the students campaigned against Saturday classes. Ooh, shots fired. Well, okay, two things. One, you did not pay 60 grand a year. Almost nobody does. Uh-huh. Well, we won't talk about what your mom looks like. Hmm. Yeah, yeah, yeah. Well, including, right. So, yeah. Don't get into a game of trash talking with me. You're gonna lose big time. So, yeah, 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 yeah. We do. So, and it keeps you guys awake at 8 in the morning. So, hey, what could go wrong, right? All right. So, what was I saying? The logic gates. Okay, right after that, but before we got into, oh, the administration, right? Yeah, none of you pay 60 grand a year. I love it when you're like, I don't pay 60 grand a year. Well, you don't, right? Uh-huh. Yeah, okay. Well, okay. So, yeah, yeah, okay. No, it's fair objection. And the problem, well, this is oversimplifying it. But a lot of that sort of stuff is out of our hands, right? Because the quote, how much your parents made thing is a federal question, not a college question, right? The FAFSA is, so take it up with your senators and congressmen, kind of thing. Yeah, no, you guys are right. I mean, higher ed pricing and economics is not an easy question, and it's one that, um, I mean, I'll give you maybe a good example of how things have changed. So when, I mean, this is maybe not quite true when I was in college, but you know, my parents or well, okay, my dad didn't have to pay to college. Well, he did pay for it. He paid for it with 15 years in the Marine Corps. okay? But you know, people of that era, late 70s, 80s, and so on, how did they pay for college for the most part? Huh? You worked over the summer. You worked over the summer, you made enough money to pay your tuition for the following year and have some pocket change for pizza and haircuts and stuff like that, right? And beer, right? And then the next summer, what did you do? You did the same thing over again, right? And so the fundamental problem from an economic standpoint is, has the cost of higher education gone up? Yes, but it's gone up much faster than the rate at which wages have increased, right? And so there's a mismatch between what you guys are able to earn over the summer and what higher education costs that used to be pretty much equal, right? And it's no longer the case. So anyway, all right, well, let's get back to computing since that's what we're here to talk about. So if it's equal to 1 or 2, then what's the answer? Oh, okay. The input is asking which Fibonacci do I want. So if I ask what's the first one, then it's 1. And if I ask what's the second one, it's also 1. Okay, good. All right. If it's not 1 or 2, what do I need to return? Well, how do I get the next Fibonacci number? So how did you get 3, for example? Okay. And so if I added, if I wanted to get the number 2 here, what am I doing? 1 plus 1, but what I'm really doing is saying, what's the number before and the number before that? Okay. So what would I be saying here? If I wanted to know what the third Fibonacci number is, that would be the number 2, right? That's the third one in the list. Okay. So Fibonacci of 3 would be, is 3 equal to 1 or 2? No. So what do I return? I return fib of 2 plus fib of 1. Well, what is fib of 2? What is fib of 1? And 1 plus 1 is 2 last time I checked. Okay, does that make sense? All right, so let's run this and make sure that everything worked. You guys ready for me to run it? Yeah? Okay. Oh, good. I'm getting you guys trained. All right, so I need to quit so I can reload it. All right, so from factorials, import star. All right, and so then I did a fib of, well, let's just test. Fib of 1 is 1, fib of 2 is 1, looking good. Fib of 3, the third Fibonacci is 2, 3, 5, and so on. Yeah, and in fact, what I can do here, so you see how it kind of slowed down there? Okay, why did that happen? Well, it's because it was having to recurse so much. In fact, it's still recursing here, right? So I've programmed this recursively, which for this particular function is really inefficient, okay? Because if I wanted to know what the 50th Fibonacci is, then I'm on the fly recomputing the 49th, 48th, 47th, 46th, all the way down to the very beginning, okay? What would be a much more logical way to do this would be to compute them in sequence and just stop when I hit the number that I want, okay? Or even better, pre-compute a whole bunch of these and kind of store them in a table somewhere that I could just look up off of, okay? That'd be a lot more efficient, okay? But from the standpoint of sort of illustrating how recursion works, this is a good example function, okay? And in fact, this is one that my CS241 guys, one of their assignments was to write this is like a month and a half ago, but to write a function that did the Fibonacci's both iteratively and another one that did it recursively. So sort of two ways to get at the same answer. And they don't know it yet, but they're going to get to do this again, both iteratively and recursively in assembly, which is going to make their minds explode, especially the recursive one. Yeah, it'll be great. The key is keep track of your link register and you'll be good, okay? So anyway, so it's still running, okay? And the further down the line we go, it's going to get slower and slower and slower, okay? And the reason is that, so for example, the number that's at the bottom, that 39088, blah, 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 right? Okay, that one, it's needing to know the values of all the previous numbers, but it hasn't remembered them. So it's recomputing stuff that's already computed in the past. That's not very efficient. Okay, so this is a monumentally bad way to program the Fibonacci's from an efficiency standpoint. Okay, from an understanding how recursion works, this is great. Okay, so do you guys sort of see the issue here? It's yeah, and all the way down, and so it's recomputing that 39088 blah 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 every time it goes on, right? Rather than computing it once, storing that thing, and then just using it when it needs it. Okay, so this kind of illustrates then, and is sort of maybe a good segue for what we'll start talking about on Friday. Okay, which is basically how can we measure or talk about how efficient a given piece of code is going to be, okay, or a given procedure, okay? Now, we started talking about recursion. How did we start talking about recursion? What was the very first thing we did? Well, we started talking about recursion, right? You see what I did there, right? Yeah. Yeah, okay. So what was the very first thing we did Wednesday last week? We did look up the definition of recursion. Then what did we do after that? We played then we looked, yeah, oh, you got me, right? He's like, well, then we looked up the definition of recursion. I'm like, well, actually, yes, that's true. We did that, right? No, we played the Towers of Hanoi game, right? Okay, and we played a game because it was a good way to kind of get our feet wet and figure out what the heck are we even talking about here. All right, so with the algorithm analysis, we're going to do the same sort of thing to start out, okay? So Friday, we're going to start with playing cards, okay? And I'm going to wreck you guys and hold them. No, not really. We're not going to play poker, okay? So yeah, so what we want to understand is here, right? If I ask what's the fifth Fibonacci number, that takes some amount of work to figure out, okay? If I want to ask what's the 10th Fibonacci number, that also takes some amount of work to do, okay? 10 is twice 5. Does it take me twice as much work to do 10 Fibonacci of 10 versus Fibonacci of 5? Does it take me more than twice as much work, or maybe less than twice as much work? Can we kind of quantify if I double the number of my input, then is the amount of work that I need to do double? Is it more than double? Is it like double squared, right? How could I kind of quantify that for different sorts of programmatic things? Okay, so does that kind of make sense what the question is? Okay, so we'll do this starting with playing cards, okay, because a good example of this sort of thing would be if I hand you a stack of cards, okay, and I ask you to sort them, that's going to take some amount of time, right? All right, let's say I hand you a box full of stacks of cards and I ask you to sort them. Well, is sorting 10 decks of cards 10 times harder than sorting one deck of cards? Okay, yeah, but that's assuming that the decks are separate when you start. What about if I hand you a box full of just jumbled up cards? I mean, obviously this is a little bit ridiculous, but it's going to be way more work. So let's say I hand you a box that has 10 decks of cards jumbled up in it. That would take you way more effort than just sorting one deck of cards 10 times. Okay, huh? If they're not already sorted to begin with. Or, sorry, meaning like if I handed you a box that had 10 decks of cards that were rubber banded together and each rubber banded set was all shuffled, then you could just say, okay, I've got this set of cards, this deck, I'll get them in order, then I'll get another deck and do the same thing. That would only take you 10 times as much as an individual deck, right? But what about if all the cards were just in some big mess? You'd have to sort them and also find the needed cards until you got a deck done. But then you would still have a pile of cards, right? Does that make sense? Oh, well, sort them into complete decks that are in order, right? Well, yeah, you could do that, right? But let's say that you did that. Let's say, okay, I'm going to get all the two of hearts here, and then I'm going to get all the two of diamonds, and then well, that takes you some amount of work, and then you have to build the decks.